Hello everyone. Today I will present the final review for the linear systems. In this presentation, we will quickly review the eight main concepts of the course. The topics are connected together. We start with open loop and closed loop control. Then we look at stability tools such as Routh-Lucas and Routh-Hurwitz. Then we move to state space idea such as eigenvalues, controllability, and observability. The main goal is to understand how the system behaves and how we analyze its stability and how we decide whether control or state estimation is possible. So the big picture here, first we model the system, then analyze the system, and then we understand what control do. Okay, open loop control. In open loop control, the control input is planned from the model and applied without measuring the output for correction during operation. And because there is no feedback path, the system depends on planned input and the model assumptions. So under assumed condition, the designed input is intended to achieve the desired behavior without using output feedback. Okay, control concept number 2, or the final concept number 2 is closed loop control. Unlike open loop, here we use feedback. We measure the actual output YT and compare it with our reference RT. So this creates an error signal ET, and the controller uses this error to adjust input automatically and fix any mistakes. Okay, moving to concept number 3, Routh-Lucas. This is a graphical tool. It helps us to use the closed loop poles move. Then we change a system gain like K. So here we need to remember the main rule. If poles are in the left half plane, the system is stable. If the closed loop poles are complex, the response usually has oscillation. Okay, concept 4, Routh-Hurwitz criterion. Sometimes we want to check the stability without doing the hard math to find the exact roots. So we use this method. We take the characteristic polynomial and build a table called Routh array. So we only look at the first column, number of signs or number of sign changes in this column equals to the number of unstable poles in the right half plane. Okay, and now we talk about state space modeling. Here we describe our system using matrices instead of transfer function. So we use two main equations, x dot equal to ax plus bu. Second output, this is the states equation, and the second is the output equation, y equal to cx plus du. this is a very powerful method or a very powerful way, and we can model any physical system, including mechanical and electrical systems we show here. Okay, concept number 6 is eigenvalues. To understand the natural behavior of our state space model, we look at matrix A. We find the eigenvalues by solving the determinant of lambda I minus A equal to 0. So eigenvalues act just like poles, and the real part decides if the response grow or decay. If all eigenvalues are in the left hand or left half plane, our system is stable. Okay, concept number 7 is the controllability. The main question here is, can our input move the system to any state we want? Or a better way to say this, can the input influence all independent state directions? So to answer this, we build a controllability matrix. This is actually C Greek letter, and so we build the controllability matrix using matrix B and A. If this matrix has full rank, which means the rank is equal to n, then yes, the system is fully controllable. Okay, concept number 8 is observability. The question here, can we understand the whole internal state just by looking at the output? And sorry, this is also a Greek letter like O. This is just for simplification. So we build the observability matrix using C. Here we build the observability matrix using C and the matrix A. If this matrix has full rank, then the system is fully observable. Okay, finally here, the final review map. Here we show all the concepts together. We start with the system types, open and closed loop. Then we can model them using state space form. From there, we find the eigenvalues to understand the system, use root locus and or root roots for stability, and finally check controllability and observability. Okay, here we show Python examples based on the concepts in the final. So here I used a package called Python package called control. So we can build a state space model, calculate the eigenvalues, simulate the step response, draw the root locus, and check controllability and observability. So here we can visually see and understand the math idea appear in the system behavior. And here I show how to build a simple state space model. First, we define the matrices A, B, C, D, and then we create the state space system using this SS, and then after that we calculate the eigenvalue of A we use linear algebra from NumPy. So the plot to the right shows these eigenvalues in the complex plane, and their location tell us the natural behavior of the system. So if the eigenvalues are in the left half plane, the mode decay. If one eigenvalue in the right half plane, the system become unstable. And here we show also the step response. So this is useful because the stability, we can see the response shape. And so here I only show example for the controllability and observability and how we perform it within Python or using the control package. And this is using how to draw the root locus using control package as well. And the last thing here, I show another code which I will provide in the reference I worked on, which we show here the concept of the controllability, and we show how to develop the root locus, state feedback, open loop versus closed loop, and root forward sign changes for the right half plane. The code is available here. Okay, to connect the main purpose of the review is the open loop and closed loop describe how the input is created. Root locus and root horots help us analyze stability. State space modeling gives us internal model. Eigenvalue describe natural behavior, and controllability tells us that the input can influence, and observability tells us what the output can show or reveal. And thank you very much for your time and for the listening to my review.